xLSTM, Extended Long Short-Term Memory Abstract. In the 1990s, the constant error carousel and gating were introduced as the central ideas of the long short-term memory, LSTM. Since then, LSTMs have stood the test of time and contributed to numerous deep learning success stories. In particular, they constituted the first large language models, LLMs. However, the advent of the transformer technology, with parallelizable self-attention at its core, marked the dawn of a new era, outpacing LSTMs at scale. We now raise a simple question. How far do we get in language modeling when scaling LSTMs to billions of parameters, leveraging the latest techniques from modern LLMs, but mitigating known limitations of LSTMs? Firstly, we introduce exponential gating with appropriate normalization and stabilization techniques. Secondly, we modify the LSTM memory structure, obtaining 1. xLSTM with a scalar memory, a scalar update, and new memory mixing. 2. MLSTM that is fully parallelizable with a matrix memory and a covariance update rule. Integrating these LSTM extensions into residual block backbones yields xLSTM blocks that are then residually stacked into xLSTM architectures. Exponential gating and modified memory structures boost xLSTM capabilities to perform favorably when compared to state-of-the-art transformers and state space models, both in performance and scaling. Figure 1. The extended LSTM xLSTM family. From left to right, 1. The original LSTM memory cell with constant error carousel and gating. 2. New xLSTM and MLSTM memory cells that introduce exponential gating. xLSTM offers a new memory mixing technique. LSTM is fully parallelizable with a novel matrix memory cell state and new covariance update rule. 3. MLSTM and residual blocks yield xLSTM blocks, xLSTM blocks. 4. Stacked LSTM architecture. 1. Introduction. The long short-term memory, LSTM, ideas were introduced to overcome the vanishing gradient problem of recurrent neural networks. The constant error carousel is the additive update of the cell state by cell inputs moderated by sigmoid gates. The input gate and the forget gate control this update, while the output gate controls the output of the memory cell, i.e., the hidden state. The cell state is normalized or squashed by psi, and then output gating gives the hidden state. LSTMs have been successfully applied to various domains and prevailed over text generation until the dawn of transformers. The effectiveness of LSTMs has been demonstrated in numerous sequence-related tasks, such as generating text, generating handwriting, generating sequence-to-sequence translation, evaluating computer programs, generating image captions, generating source code, rainfall runoff modeling, and models for flooding warnings. In reinforcement learning, LSTMs are the best-performing sequence models, e.g. the AlphaStar model for StarCraft 2, the OpenAI 5 model for Dota 2, and models of the magnetic controller for nuclear fusion. LSTMs excel at learning abstractions, i.e., adeptly extracting semantic information and storing it in their memory cells, which for LSTMs, still being evident by number and syntax neurons and disentanglement neurons. LSTMs are still used in highly relevant applications and have stood the test of time. Figure 2. LSTM limitations. Left, nearest neighbor search problem in terms of mean squared error, MSE. Given a reference vector, a sequence is scanned sequentially for the most similar vector with the objective to return its attached value at sequence end. LSTM struggles to revise a stored value when a more similar vector is found. Our new xLSTM overcomes this limitation by exponential gating. Right. Rare token prediction. The perplexity PPL of token prediction on Wikitext 103 in buckets of token frequency. LSTM performs worse on predicting rare tokens because of its limited storage capacities, whereas our new xLSTM solves this problem via a matrix memory. Despite their tremendous successes, LSTMs have 3 main limitations. 1. Inability to revise storage decisions. We exemplify this limitation via the nearest neighbor search problem. Given a reference vector, a sequence must be scanned sequentially for the most similar vector in order to provide its attached value at sequence end. The left panel of Figure 2 shows the mean squared error at this task. LSTM struggles to revise stored value when a more similar vector is found, while our new xLSTM remedies this limitation by exponential gating. 2. Limited storage capacities, i.e., information must be compressed into scalar cell states. We exemplify this limitation via rare token prediction. In the right panel of Figure 2, The perplexity of token prediction on Wikitext 103 is given for buckets of different token frequency. LSTM performs worse on rare tokens because of its limited storage capacities. LSTM performs worse on rare tokens because of its limited storage capacities. Our new xLSTM solves this problem via matrix memory. 3. Lack of parallelizability due to memory mixing, i.e., the hidden connections between hidden states from one time step to the next, which enforce sequential processing. These limitations of LSTM have paved the way for the emergence of transformers in language modeling. What performances can we achieve in language modeling when overcoming these limitations and scaling LSTMs to the size of current large language models? 2. Extended long short-term memory. To overcome the LSTM limitations, extended long short-term memory, xLSTM, introduces two main modifications to the LSTM idea of equation 1. Those modifications, exponential gating and novel memory structures, enrich the LSTM family by two members. 1. The new xLSTM with a scalar memory, a scalar update, and memory mixing. And 2. The new mLSTM with a matrix memory and a covariance outer product update rule, which is fully parallelizable. Both xLSTM and mLSTM enhance the LSTM through exponential gating. To enable parallelization, the mLSTM abandons memory mixing, i.e. the hidden recurrent connections. Both mLSTM and xLSTM can be extended to multiple memory cells, where xLSTM features memory mixing across cells. Further, the xLSTM can have multiple heads without memory mixing across the heads, but only memory mixing across cells within each head. This introduction of heads for xLSTM, together with exponential gating, establishes a new way of memory mixing. For mLSTM, multiple heads and multiple cells are equivalent. Integrating these new LSTM variants into residual block modules results in xLSTM blocks. Residually stacking those xLSTM blocks in architectures provides xLSTM architectures. See Figure 1 for the xLSTM architecture with its components. 2.1. Review of the long, short-term memory. The original LSTM idea, Hochreiter 1991, Hochreiter and Schmidhuber 1997 A.B., introduced the scalar memory cell as a central processing and storage unit that avoids vanishing gradients. Hochreiter 1991, Hochreiter et al. 2000 through the constant error carousel, the cell state update. The memory cell contains three gates: input, output, and forget gate. The forget gate has been introduced by Gers et al. 2000. The LSTM memory cell update rules at time step TR. Cell state 2, hidden state 3, cell input 4, input gate 5, forget gate 6, output gate 7. The weight vectors, W sub x, W sub r, W sub g, and W sub o, correspond to the input weight vectors between inputs x sub t and cell input gate, forget gate, and output gate, respectively. The weights r sub i, r sub f, r sub o correspond to the recurrent weights between hidden state h sub t minus 1 and cell input gate, forget gate, and output gate, respectively. B sub x, B sub r, B sub g, and B sub o are the corresponding bias terms. Psi and psi tilde are the cell input and hidden state activation functions, typically tanh. Psi is used to normalize or squash the cell state, which would be unbounded otherwise. All gate activation functions are sigmoid, i.e., sigma tau equals 1 divided by 1 plus e to the power of minus tau. In later formulations, multiple memory cells were combined in a vector, which allows the usage of recurrent weight matrices to mix the cell outputs of memory cells. Greff et al. 2015. For more details, see Appendix A.1. Ablation studies showed that all components of the memory cell are crucial. Greff et al. 2015. 2.2. LSTM. To empower LSTMs with the ability to revise storage decisions, we introduce exponential gates read together with normalization and stabilization. In particular, input and forget gates can have exponential activation functions. For normalization, we introduce a normalizer state that sums up the product of input gate times all future forget gates. The xLSTM forward pass is C formulas 8 through 14. We broadcast the original LSTM gating techniques, that is, input and or hidden dependent gating plus bias term, to the new architectures. Exponential activation functions can lead to large values that cause overflows. Therefore, we stabilize gates with an additional state m sub t, see formulas 15 through 17. We show in Appendix A.2 that replacing by and by in the forward pass does neither change the output of the whole network nor the derivatives of the loss with respect to the parameters. New memory mixing, xLSTM, can have multiple memory cells like the original LSTM. Multiple memory cells enable memory mixing via recurrent connections from hidden state vector to memory cell input and the gates respectively. A new aspect in memory mixing is the effect of exponential gating. The new xLSTM can have multiple heads with memory mixing within each head but not across heads. The introduction of heads for xLSTM, together with exponential gating, establishes a new way of memory mixing. 2.3 mLSTM. To enhance storage capacities of LSTMs, we increase the LSTM memory cell from a scalar to a matrix. Hence, retrieval is performed via a matrix multiplication. At time t, we want to store a pair of vectors, the key and the value. We use the transformer terminology. Later, at time t plus tau, the value should be retrieved by a query vector. This is the setting of bidirectional associative memories, BAMs. The covariance update rule is C sub t equals C sub t minus 1 plus V sub t k sub t wedge. We assume a layer norm before projecting inputs to keys and values, therefore they have zero mean. The covariance update rule is optimal for a maximal separability of retrieved binary vectors, which is equivalent to a maximal signal-to-noise ratio. Higher separability is possible when limiting retrieval to pairwise interactions and conceding quadratic complexity like attention. The covariance update rule is equivalent to fast wait programmers, which have later been equipped with a constant decay rate multiplied to and a constant learning rate multiplied to key. In this spirit, we integrate the covariance update rule into the LSTM framework, where the forget gate corresponds to decay rate and the input gate to the learning rate, while the output gate scales the retrieved vector. For this matrix memory, the normalizer state is the weighted sum of key vectors, where each key vector is weighted by the input gate and all future forget gates. Again, the normalizer state keeps record of the strength of the gates. Since the dot product between query and normalizer state can be close to 0, we use the absolute value of this dot product and lower bound it by a threshold, typically 1.0, as done previously. The mLSTM forward pass is see formulas 19 through 27. mLSTM can have multiple memory cells like the original LSTM. For mLSTM, multiple heads and multiple cells are equivalent as there is no memory mixing. In order to stabilize the exponential gates of mLSTM, we use the same stabilization techniques as for xLSTM, see equation 15. Since the mLSTM has no memory mixing, this recurrence can be reformulated in a parallel version. For more details, we refer to Appendix A.3. 2.4. xLSTM architecture. xLSTM blocks. An xLSTM block should non-linearly summarize the past in a high-dimensional space to better separate different histories or contexts. Separating histories is the prerequisite to correctly predict the next sequence element, such as the next token. We resort to Cover's theorem, which states that in a higher dimensional space, non-linearly embedded patterns can more likely be linearly separated than in the original space. We consider two residual block architectures: a residual block with post-up projection, like transformers, which non-linearly summarizes the past in the original space, then linearly maps into a high-dimensional space, applies a nonlinear activation function, and linearly maps back to the original space. See left panel of Figure 3 and depicted in Figure 9 in the appendix. A residual block with pre-up projection, like state space models, which linearly maps to a high-dimensional space, non-linearly summarizes the past in the high-dimensional space, and then linearly maps back to the original space. For an xLSTM block containing an SLSTM, we mostly use the post-up projection block. For a residual mLSTM block or an mLSTM, we use the pre-up projection block since the memory capacity becomes larger in the high-dimensional space. See left panel of Figure 3 and third column in Figure 1, or Figure 9 in the appendix for more details. Figure 3, xLSTM blocks. Left, a residual SLSTM block with post-up projection, like transformers. The input is fed into an SLSTM, with an optional convolution, followed by a gated MLP. Right, a residual mLSTM block with pre-up projection, like state space models. mLSTM is wrapped inside two MLPs via a convolution, a learnable skip connection, and an output gate that acts component-wise. See Figure 9 and Figure 10 in the appendix for details. xLSTM architecture. An xLSTM architecture is constructed by residually stacking building blocks. We rely on the most commonly used pre-layer norm residual backbones as used in contemporary large language models. See last column in Figure 1. 2.5. Memory and speed considerations. Contrary to transformers, xLSTM networks have a linear computation and a constant memory complexity with respect to the sequence length. Since the xLSTM memory is compressive, it is well suited for industrial applications and implementations on the edge. The memory of mLSTM does not require parameters, but is computationally expensive through its D by D matrix memory and D by D update. We trade off memory capacity against computational complexity. Nevertheless, the computations can be done in parallel on GPUs. Therefore, these computations have only a minor effect on the wall clock time. While mLSTM is parallelizable analog to flash attention in GLA, xLSTM is not parallelizable due to the memory mixing hidden connections. However, we developed a fast CUDA implementation with GPU memory optimizations to the register level, which is typically less than 2 times slower than mLSTM. 3. Related work. Linear attention. Several methods have been suggested to overcome the quadratic complexity in terms of context length of the transformer and make attention linear in the context length. The synthesizer learns synthetic attention weights without token-token interactions. Linformer realizes self-attention by a low-rank matrix and even linearly approximates it. Linear transformer linearly approximates the attention softmax by positive orthogonal random features approach. Attention has been replaced by fast long convolutions in the structured global convolution and the hyena hierarchy. State space models. Recently, state space models became very popular since they are linear in the context length and show promising performance compared to transformers. One of the first proposed models was structured state space sequence model, followed by diagonal state space model, gated state space models, S5 model, bidirectional gated SSM, H3 model, and Mamba. Recurrent neural networks. Recurrent neural networks have been suggested to replace transformer and attention due to their linearity in the context length. RNNs with deep linear recurrent units showed promising results for language modeling, as did hierarchically gated linear RNN and HGRN2. A well-known RNN approach to large language modeling is RDUKV, showcasing competitive performance to transformers. Gating. One of the key ideas of LSTM is gating, which was rediscovered and reinterpreted in many recent approaches. Gating was used in HGRN, HGRN2, GLA, GSS models, bidirectional gated SSM, moving average equipped gated attention, RWKV, and Mamba. Covariance update rule. To enhance storage capacities, we equip the mLSTM cell with a matrix memory with a covariance update rule. Other methods which build on such an update mechanism are fast wait programmers, RWKV5 and RWKV6, retention, linear transformer, and H2, most related. Conceptually, the closest models to xLSTM are retention, RWKV, and HGRVE. These models share the concepts matrix memory and/or gating. However, in contrast to the new xLSTM, these approaches do not allow memory mixing. Memory mixing enables to solve state tracking problems, and therefore LSTMs are more expressive than state space models and transformers. State tracking is required to evaluate code or to track entities in a long narrative. Residually stacking architectures. Like almost all contemporary large deep learning models, xLSTM architectures are constructed by residually stacking building blocks. This construction enables deep convolutional networks and transformers. Transformers are the ultimate force behind large language models like GPT, ChatGPT, GPT-4, Megatron LLM, Gopher, Ernie 3.0 Titan, GLAM, Chinese M6, Multilingual Alexa TM, OP, Chinchilla, Bloom, GLM LambDA, and Gemini. 4. In this section, we experimentally evaluate xLSTM and compare it to existing methods with a focus on language modeling. We investigate xLSTM's specific capabilities on synthetic tasks in Section 4.1. Then, in Section 4.2, we compare the validation set perplexity of various current language modeling methods that were trained on 1.5 billion tokens from Slim Pajama. On the same dataset, we perform ablation studies for xLSTM. Then, we assess the scaling behavior of the different methods analogous to Kaplan and Brown. In Section 4.3, we conduct a more thorough language modeling experiment. We compare xLSTM and the best performing methods from Section 4.2 against the long document benchmark Paloma. In Section 4.4, we assess how well the methods perform in extrapolating to longer contexts. Secondly, we test the methods via validation perplexity and next token performance on downstream tasks. Fourthly, we again assess the scaling behavior of the different methods, but now with 20 times more training data. For all experiments, we use the notation xLSTM for the ratio AB of MLSTM-based versus SLSTM-based xLSTM blocks. For example, xLSTM 7.1 means that out of 8 blocks, 7 are MLSTM-based blocks and 1 is an SLSTM-based block. For a common total block number of 48, this translates to 6 SLSTM-based blocks and 42 MLSTM-based blocks. Further, for all experiments, we use pre- and post-up projection blocks for MLSTM and SLSTM respectively. 4.1. Synthetic tasks in long-range arena. First, we test the effectiveness of xLSTM's new exponential gating with memory mixing on formal languages. Then, we assess the effectiveness of xLSTM's new matrix memory on the multi-query associative recall task. Finally, xLSTM's performance at processing long sequences in the long-range arena is evaluated. Test of xLSTM's exponential gating with memory mixing. We test xLSTM's new exponential gating with memory mixing, which should enable it to solve state tracking problems. We implement and extend the formal language tasks from to enable multi-length training for length extrapolation. For a detailed description of all tasks and extended results, see Appendix B 1.1. We compare xLSTM to other methods including transformers, state space models, and recurrent neural networks. The accuracy of the tested methods is evaluated on those tokens relevant to the task. The accuracy is scaled between 0, random, and 1, perfect. We compare two block architectures of the following methods on these tasks: xLSTM, i.e. only SLSTM, xLST7.1, Llama, Mamba, RWKV, Retention, Hyena, LSTM, and LSTM in transformer blocks, LSTM block. The results of this experiment are shown in Figure 4. Models such as transformers or state space models without memory mixing, no state tracking, cannot solve e.g. regular grammars like the parity task. Figure 4. Test of xLSTM's exponential gating with memory mixing. Results are given by the scaled accuracy of different models at solving formal language tasks, of which some require state tracking. The different tasks are grouped by the Chomsky hierarchy. This result is in agreement with findings that transformers and state space models are fundamentally less powerful than RNNs. Test of xLSTM's memory capacities on associative recall tasks. In this experiment, we test xLSTM's new matrix memory in terms of the memory capacity on the multi-query associative recall task. For each sequence, key value pairs are randomly chosen from a large vocabulary which must be memorized for later retrieval. To enhance the difficulty of the original task, we increase the number of key value pairs up to 256, and extend the context length up to 2048. Thus, we have broader tests for the memory capacities of different models. We compare two block architectures of Llama, Mamba, RWKV5, RWKV6, xLSTM11, and xLSTM10. The models are evaluated by the accuracy at recalling the pairs. Since transformers, for example, Llama, have a memory that is exponential in the coding dimension, they constitute the gold standard at this task. Results are shown in Figure 5. xLSTM11 performs best among all non-transformer models, also for small models. Interestingly, the LSTM block does not diminish the memory capacity but rather leverages it, which becomes evident at the most difficult task with 256 key value pairs. Additional results are presented in Appendix B 1.2, where extrapolation analyses indicate that xLSTM's enhanced memory capacities also pertain when extrapolating to contexts that are longer than those seen during training. Figure 5. Test of memory capacities of different models at the multi-query associative recall task, with context length 2048. Each panel is dedicated to a different number of key value pairs. The x-axis displays the model size, and the y-axis the validation accuracy. Test of xLSTM's long context capabilities on long-range arena. To assess xLSTM's performance on long sequences and large contexts, we compare different methods on the long-range arena. xLSTM demonstrates consistent, strong performance on all of the tasks, suggesting that the xLSTM architecture is remarkably efficient in handling different aspects of long context problems. For more details, see Appendix B 1.3. 4.2 Method Comparison and Ablation Study. The main question of this paper is, what can we achieve in language modeling when scaling up the new LSTM variants? Therefore, we train xLSTMs, transformers, state space models, and other methods on 15 billion tokens from Slim Pajama in an autoregressive language modeling setting. We We compare the trained models on the validation set. Finally, we perform ablation studies for xLSTM. Table 1. Method comparison on next token prediction when trained on 15B tokens from Slim Pajama. Best validation perplexities within model classes, i.e. transformers, LSTMs, SSMs, RNNs, and linear transformers are underlined, and overall best is in bold. For each model class, the best performing methods are later used in section 4.3 for LLM training. xLSTMs with new memory, xLSTM-WO and xLSTM-7.1 perform best. Comparing xLSTM to other methods. For comparison, we train models on 15 billion tokens from Slim Pajama. The trained models are evaluated by their perplexity on the validation set. We compare the following models: xLSTM, GPT-3 Transformer, Llama, Transformer, H3 SSM, Mamba, RWKV4, RWKV6, GLA, Linear Transformer, HGRN, and xLSTM-T. The models we trained with mixed precision except RWKV5, RWKV6, GLA, HGRN2, where mixed precision training was not supported by the reference implementation. We categorize the models into transformers, state space models, and recurrent neural networks, together with linear transformers. Linear transformers are linear methods that substitute the transformer attention mechanism. The models match a GPT-3 model with 350 million parameters, i.e., the embedding dimension 124 and residual blocks. Only GPT-3 uses shared weights for token and output embeddings, whereas the fewer parameters. The results in Table 1 show that xLSTM outperforms all existing methods in validation perplexity. For details, see Appendix B.2. Figure 6 shows the scaling behavior for this experiment, indicating that xLSTM will also perform favorably for larger models. Ablation studies. Table 1 and Figure 6 demonstrate that xLSTM achieves excellent results at language modeling when being trained on 15 billion tokens from Slim Pajama. Thus, it is only natural to ask which of the elements of xLSTM is responsible for the improvements over vanilla LSTM performances, evoking an ablation study of the individual new xLSTM components. For doing so, we morph a vanilla LSTM architecture step by step into an xLSTM architecture. First, we integrate LSTM layers into pre-layer norm residual backbones. Second, we extend this to a post-up projection block. Then we add exponential gating, and finally the matrix memory. The ablation studies attribute the strong performance improvement to both the exponential gating and the matrix memory. Additionally, since gating is an ever-occurring topic in RNNs and state space models, we ablate different gating mechanisms. In Table 2, we conclude that having each gate learnable and influenced by the input has an incremental positive effect. Additional studies on the individual backbone components are discussed in Appendix B.2. Figure 6. Method comparison on next token prediction when trained on 15 billion tokens from Slim Pajama. Performance measure in validation perplexity for the best methods of each model class, see Table 1, are reported. The performance degradation of xLSTM 7:1 at 2.7 billion is due to initially slower training convergence that leads to an especially undertrained model. xLSTM is the best method at all sizes. Ablation studies on the new xLSTM components. Table 2. Ablation studies. Top. Ablation studies on the new xLSTM components, contributing the strong performance improvement of xLSTM over vanilla LSTM to both the exponential gating and the matrix memory. Bottom. Ablation studies on different gating techniques. We consider an xLSTM 10:1 with sigmoid forget gate and exponential input gate. Bias initialization on means that the forget gate is set to 1, 3, 6 indicates that these values are taken equidistant in the respective interval, and N0, 0.1 values are randomly chosen from a Gaussian with mean 0 and standard deviation 0.1. PPL denotes validation perplexity. The first two lines correspond to models similar to linearized attention, line 4 to retention, line 5 to RWKV5, and line 6 to RWKV6. Dependencies of the gates on the input lead to better performance. 4.3. xLSTM as large language model. We culminate this study in large-scale language modeling experiments, testing the potential of xLSTM as an LLM. We therefore increase the amount of training data and train on 300 billion tokens from Slim Pajama. The same number of tokens is used in Mamba and Griffin. We compare xLSTM, RWKV4, Llama, and Mamba, which were selected as the best-performing methods in their respective method classes, in the model comparison in Section 4.2. We train different model sizes, 125 million, 350 million, 760 million, 1.3 billion. Test all models for length extrapolation capabilities and evaluate their performance on the validation set. We assess their performance on downstream tasks, test their performance in language modeling on 471 text domains of the Paloma benchmark, and finally investigate their scaling law behavior. Sequence length extrapolation. First, we test the sequence length extrapolation for 1.3 billion sized large models of xLSTM, RWV4, Llama, and Mamba. All models are trained on context length 2048 and then tested for context lengths up to 16,384. See Figure 7 for the results. In contrast to other methods, xLSTM models maintain low perplexities for longer contexts. Figure 7. Sequence extrapolation in language modeling. This is a comparison of 1.3 billion sized large models of xLSTM, RWKV4, Llama, and Mamba at next token prediction on the Slim Pajama validation set after training on 300 billion tokens from Slim Pajama. Models are trained with context length 2048 and then tested for context lengths up to 16,384. Left, token perplexities evaluated at different context lengths. In contrast to other methods, xLSTM models remain at low perplexities for longer contexts. Right? Prediction quality when extrapolating to long context sizes in terms of validation perplexity, PPL. xLSTM yields the best PPL values, best in bold, second best underlined. Validation perplexity and downstream tasks. Secondly, for all model sizes, we evaluate the performance of xLSTM, RWKV4, Llama, and Mamba models on the Slim Pajama validation set for next token prediction and on downstream tasks that measure common sense reasoning. The third column of Table 3 lists the validation set perplexities of different methods. Both xLSTM 1.0 and xLSTM 7.1 are the best models for all model sizes with respect to the validation set perplexity. The other columns of Table 3 provide the performance on downstream tasks. In the vast majority of tasks and across all model sizes, xLSTM is the best method. Only on the ARC task, Mamba is in some cases the best method. For details, see Appendix B.3. Performance on Paloma language tasks. Thirdly, for all model sizes, we test the next token prediction performance of xLSTM, RWKV4, Llama, and Mamba models on Paloma language tasks. We measure the performance by the perplexity for next token prediction on 471 test domains, which range from nighttimes.com to Arsh Depression on Reddit. Table 4 shows token prediction perplexity grouped into language modeling, first 7 columns, and fine-grained domain benchmarks, last 5 columns. xLSTM 1.0 performs better than xLSTM 7.1 on these language tasks. xLSTM 1.0 has in 568 out of 571 99.5% text domains a lower perplexity than Mamba, in 486 out of 571 85.1%, a lower perplexity than Llama, in 570 out of 571 99.8%, a lower perplexity than RWKV4. For details, see Appendix B.3. Table 3. Validation set perplexity and downstream tasks. Comparison of xLSTM, RWKV4, Llama, and Mamba on the validation set at text token prediction and on downstream tasks after training on 300 GB tokens from Slim Pajama. Model sizes are 125M, 250Ms, 760Ms, and 1.13b. The second column shows the actual number of parameters. The 7 text domains are grouped into a language modeling task, 7 columns, and fine-grained domain benchmarks, further 5 columns. The last column shows the average perplexity across all of these tasks. Best model per model size is given in bold and the second best is underlined. xLSTM yields the best performance. Table 4, Performance on Paloma language modeling tasks. Comparison of xLSTM, RWKV4, Llama, and Mamba by the perplexity of next token prediction on the Paloma language benchmark after training on 300 GB tokens from Slim Pajama. Model sizes are 125M, 250M, 760Ms, and 1.13b. The second column shows the actual number of parameters. The 571 text domains are grouped into a language modeling task, 7 columns, and fine-grained domain benchmarks, further 5 columns. The last column shows the average perplexity across all of these tasks. Best model per model size is given in bold, and the second best is underlined. xLSTM yields the best performance. Scaling laws. Fourthly, we assess the power law scaling behavior, which allows us to extrapolate the performance to larger model sizes. Figure 8 presents the scaling behavior. All models share a similar scaling behavior, but with different offsets. RWKV4 performs worst, followed by Llama and Mamba. xLSTM is better than Mamba, with a similar margin to Mamba as Mamba has to Llama. The scaling behavior indicates that for larger models, xLSTM will continue to perform favorable compared to transformers and state space models. Figure 8. Scaling laws. Next token prediction perplexity of xLSTM, RWKV4, Llama, and Mamba on the Slim Pajama validation set when trained on 300B tokens from Slim Pajama. Model sizes are 125 mem, 360 m, and 1.3b. Best models for each model class were selected. The scaling laws indicate that for larger models, xLSTM will perform well too. 5. Limitations. 1. In contrast to MLSTM, memory mixing of the xLSTM prohibits parallelizable operations and therefore does not allow a fast parallel implementation. Nevertheless, we developed a fast CUDA kernel for xLSTM, which is currently around 1.5 times slower than our parallel MLSTM implementation. 2. The CUDA kernels for MLSTM are not optimized, and therefore the current implementation is about 4 times slower than flash attention or the scan used in Mamba. Faster CUDA kernels could be obtained in the vein of flash attention. 3. The matrix memory of MLSTM has high computation complexity since D times D matrices must be processed. Still, the memory update and retrieval does not use parameters and can be parallelized using standard matrix operations. Therefore, the wall clock time overhead due to the complex memory is minor. 4. The initialization of the forget gates must be chosen carefully. 5. Since the matrix memory is independent of the sequence length, increasing the sequence length might overload the memory for longer context sizes. Still, this does not appear to be a limitation for contexts up to 16K. See section 4.3. 6. Due to the expensive computational load for large language experiments, we did neither fully optimize the architecture nor the hyperparameters, especially for larger xLSTM architectures. We anticipate that an extensive optimization process is needed for xLSTM to reach its full potential. 6. Conclusion. We have partly answered our simple question: how far do we get in language modeling when scaling LSTM to billions of parameters? So far, we can answer at least as far as current technologies like transformers or state space models. We have enhanced LSTM to xLSTM by exponential gating with memory mixing and a new memory structure. xLSTM models perform favorably on language modeling when compared to state-of-the-art methods like transformers and state space models. The scaling laws indicate that larger xLSTM models will be serious competitors to current large language models that are built with the transformer technology. xLSTM has the potential to considerably impact other deep learning fields like reinforcement learning, time series prediction, or the modeling of physical systems. Acknowledgements. We thank Sebastian Lehner, Daniel Klotz, Thomas Adler, Matthias Delago, Gerald Gutenbrunner, Fabian Pasichny, Vaihang Patil, Niklas Schmiedinger, Benedikt Alkin, Kajetan Schweigofer, Anna Zimmel, Lukas Eichberger, Lukas Hautzenberger, Bernhard Schäffi, Johannes Lehner for helpful discussions and feedback. This concludes the reading of this paper on Research to You. If you would like more papers added, please leave a comment. If you would like to be notified when more papers are available, be sure to subscribe, like, and ring the bell.